this is your Math 165 final exam review. Okay. This final exam is going to be comprehensive, right? So it will also, in addition to the new material we covered after second exam, it will also cover some questions from your exam 1 and exam 2. So the new material part is in this practice exam 3 set. So this is what we are going to go over today here in review session. And then in addition to this, you should also review your actual exam 1 and exam 2. Okay? So you will certainly see some of the questions that you had on your first and second tests again on this comprehensive final. Okay, so first let's go over some of the highly probable questions from this practice exam 3 set, and then if we have time and if you have any questions, we can go over some of the questions from your exam 1 and exam 2, okay? Your last 2 exams. All right, so this new material part covers, let's see, these topics. So let me list out some of the topics here. It covers, let's see, what does it cover? It covers these word problems, right? It begins with all of these word problems. So like, motion word problems, and distance word problems, distance or, work, motion and distance, same, work word problems. And then you will also see a variance word problem, variance. So this variance word problems means that this is an extension of ratio and proportion, right? Ratio and proportion word problems that you have already encountered, right? From one of the past tests, you've already seen these types of questions there. And then I think after that you have some, functions and model problems on functions and models, and then we have solving systems of equations, solving systems of equations. Okay, and then 2 more topics: absolute value equations and inequalities, and finally solving quadratic equations. So these are the topics we have covered after your second exam, okay? Quadratic equations. So for the older material part, you can review, you can go back to our review sessions for exam 1 and exam 2, right? And you can also review your actual exams that are handed back to you. Okay, so let's go through this, through these questions, through this list of questions one by one. And I want to begin with this one, functions and models. I will come back to these word problems in a while. So let's just work through these first, and then we'll come back to these word problems in a while. Okay. All right, it's function and models. Let's start there. Let's see, the question I am looking at is, number 9. This question here. So first you need to know what a function is, right? What a function is. So let me review that first, okay? So a relation is a rule, right? It's a rule or association, or association between x values and y values. X values and y values. Simply an association, right? Or some kind of rule. That's a relation. Okay? And now, if we make certain conditions, if we require certain criteria for this relation to satisfy, now a function is a special relation, relation where each x is associated to a unique y, right? Or in other words, that is, no x has two different y's, right? No x has two different y's. If this additional criterion is satisfied, then a relation is called a function. And both for a relation and a function, the set of x values is called the domain. Domain is the set of x values, right? And range is the set of y values. Okay. So that's what it is. So for a function to, and we can identify whether a given relation is a function or not in several different ways. There are several different ways you can check whether or not a given function is a given relation is actually a function or not. Whether or not this additional criterion is satisfied or not. We can check that. So one way of checking that is looking at the graph, right? Like in this question. So the graphical way of checking is a function verifies or satisfies the vertical line test. Vertical line test. That is, no vertical line cuts its graph. No vertical line cuts its graph at more than one point, right? At more than one point. So if you look at it, this is the same, this is equivalent to saying that no x has two different y's, right? But it's just graphical interpretation, right? A graphical way of checking that no x has two different y's. Okay, And I think when this happens, let me finish this. So I think now we can erase this part, right? So we'll go through these questions one by one again. Okay. Now, since each x has a unique y for a function, there is this functional notation we can replace y by this f of x in functional notation. Functional notation, we can replace y by f of x, and y and f of x are interchangeable, and this is read as f of x, right? It's read as f of x. And for example, this f of 2 means plugging in x equals to 2 is evaluating, right? Evaluating, evaluating f at 2, right? F at x equals to 2, which means finding the y value corresponding to x equals to 2. Okay, that's what it is. So that's a review of functions and relations. So now with this, let's answer this question here. Now let's come back to this screen here. So it says determine whether the graph illustrated represents a function, and give the domain and range of each function or relation. C, approximate the value or values of x where y equals to 2. So looking at that graph and remembering how we can check whether a given graph is a function or not, what do you think? Is it a function? It is not a function because it doesn't satisfy that vertical line test, right? If you take a vertical line, let's say at this 4, then it clearly cuts this graph at 2 points, which is one is at y equals to 2 and the other one is at y equals to -2. So the x equals to 4 line cuts at 2 y values, which means the y value is not unique, right? So it violates, it doesn't satisfy the vertical line test, so it is not a function. And it says find the domain of this function, not function, in this case just a relation. Find the domain of this relation. So the domain, according to this graph, is all the x values, right? All the x values covered in this graph start from 2 and goes all the way to infinity, right? These arrowheads indicate that it goes on forever in that direction. So the x values are 2, anything bigger than or equal to 2, right? Yeah, 2 through infinity, yes. So we can write x is bigger than or equal to 2, right? Yes? Okay. And then the next part says find the range. Range are the y values, right? What y values are covered by this graph? What do you think?
That's a negative infinity to infinity.
Yes, everything, right? All these y values are covered because, these arrowheads indicate that, it's continuing, right, in that direction. So this is, let's see, negative infinity, and then yes, we can do a type an inequality, it says. So if you want to type an inequality or a compound, so I think, let's see, negative infinity, then y infinity. No. Let's see, why? Did I think I erased y, right? Is that what they want? So type an inequality or y less than, no, what happened here? Oh, okay, here. The next one, the range is the set of all real numbers. Okay, there's that option there. Okay, all right, there we go. So now similarly we can look at another modeling this function problem, which is this number 13. No, not number 13. What number is this? Let's see. Number this one looks familiar.
Yup.
All right. Okay, so so here we have a we have a graph here, and from that graph, it's a line, right, straight line. We have to find the equation, right? Not equation. We have to find the function. Function that represents this linear model, this linear model. So again, so in functional notation, y is replaced by f of x. But if we replace f of x by y, then they are the same thing. And if you use y, it's just going to be an equation, right? So an equation of this line, straight line. So we need to recall something about linear equations. So let me do that here. So a straight line, right? Equation of a straight line. Equation of a straight line is given by this y equals to mx plus v. This formula, this is called slope-intercept form. Slope-intercept form. And in the slope-intercept form, how do you find these m and b values? So these are, for example, if this is a line, a straight line, the point where the line meets the y-axis is called the intercept, y-intercept, and the measure of how slanted the line is, which is given by this ratio of rise over run between any 2 points. Right? It doesn't matter what 2 points you choose. If you choose any 2 points on the line, x1, y1, and x2, comma y2, then between those 2 points you can find the rise and the run between those 2 points, and that the ratio of rise over run is called slope. Right? Slope is denoted by m, is rise over run, and given by this formula y2 minus y1 over x2 minus x1 whenever you have any 2 points, x1, y1 and x2, y2 on the line, right? So that's how you find slope and that's how you find the slope of a straight line. And you, in addition, if you also know the y-intercept of the line, then you can find the equation of this line in this way. And this is an equation form, right? And when we replace this y by f of x, then this is a linear model. And this is now functional or model form, right? Model form. So this is what we need to find out. We need to find the equation of the line and then replace y by f of x, or in this case h of x, right? Here, h of x, and come up with the function which describes that line, or that line or some other line. Let's see, let's read here. The following bar graph shows the maximum recommended heart rate in beats per minute, all right? So this y value is maximum recommended heart rate beats per minute, and the x values in this graph is age, right? So that's this chart here. Part A says use the straight line to determine a function that can be used to estimate the maximum heart rate h, where x is the number of years after age 20. Right? You see that there's slightly the problem, it changed slightly, right? It doesn't say x is the age, right? You see, in this chart, your x values are age, right? See this x, this is 20 means age is 20 years, age is 30 years. So these x values in this chart is age. But the problem says you want x value to be not age, but the number of years after age 20, right? See, so that means now these x values are not good for us, right? We need to shift these x values to our new x values, which represents number of years after age 20. So for us now, 20 years of age, 20 years of age is same as is x equals to 0 now, because now x represents number of years after age 20. So 30 years of age becomes x equals to 10. See that? And 40 years of age becomes x equals to 20. And that's because x is number of years after age 20. Right? If that is the case, we can now use the two values, use the 2 points on the line as 0, 200 and 10, 190, right? The y value, that is maximum recommended heart rate for x equals to 0, which corresponds to 20 years of age, is 200. The maximum heart rate for x equals to 10, that is number of years after age 20, 10, which corresponds to 30 years of age, is 190 according to this chart. And once you have any 2 points on the line like this, now we can use this formula to find the slope. So let's see. So let's call this x1, y1. Let's call this x2, y2, right? And then y2 minus y1 is 190 minus 200 over 10 minus 0, which is negative 10 over 10, which is minus 1, right? And then we also see this, this is y-intercept, right? So this is also 0, comma b. So b is 200, right? Because that's a y-intercept. So mx plus b becomes, m is negative 1 and b is 200. So negative 1x plus 200. All right. So that's the function. So let's write that, negative x plus 200. So negative x plus 200. Okay. Now the second part says use that function right there to determine the maximum recommended heart rate for a 37-year-old man, right? So now again you have to go back to x, right? If you want to find y value, you need to find the corresponding x value. For 37-year-old man, the number of years after age 20 would be, what is the x value? 17. So all we need to do is now plug in x equals to 17, and that will give us corresponding y value for that x value, which is 200 minus 17, and that is, let's see, 200 minus 17, what is that? 183, yes, 183. Okay. All right, yeah. So this is an important question. You know, some of you didn't get it correct on the quiz. All right, so the next thing I want to, the next problem I want to work out is number solving systems of equations. Let's see, number.
Was that other one on the quiz? Was that on this too? I don't know if I got 100 or not.
Which one?
That other one on that quiz, is that on here as well?
No, it's not here. Not here.
So I know I got a 50 so far.
So let's do this one, right? So we have a system of equations. So solving a system of equations is just like solving one equation, right? But instead of one equation, you have a couple of equations. The number of equations will be the same as number of variables. So in this case, you have 3 equations because you have 3 variables, x, y, and z. We need that because, you know, the goal here is to bring them down to one equation in one variable, right? So when you bring 3 equations in 3 variables down to one equation and one variable, then we know how to solve it. Okay, let's see how we can do that. Yeah, you need to play around with these equations and eliminate variable, right? The technique is to eliminate variables one by one so that only one variable remains, right? So let's see. Here it's x plus 5y equals to 15, and then 6y equals to 18, and then x plus 5z equals to 40. So you have these 3 equations in 3 variables. So what we want to do is we want to eliminate one of the variables and then bring it down to 2 variables in 2 equations in 2 variables. And again, repeat the process and bring it down to 1 equation in 1 variable. So in this case, it's easy to eliminate y because, so actually we can even divide this equation by 1 over 6 actually, and reduce it to just y equals to 3. See that? So let's call it equation number 1, let's call it equation number 2, let's call it equation number 3. You don't have to, but it just makes it easier. And let's use equation number 2, which is y value, in 1 and 3. So that immediately reduces to just 2 variables. So let's first use 2 in 1. If we do that, then you have x plus 5 times 3 equals to 15, right, like this. And let's just simplify. This is x plus 15 equals to 15, which is x equals to 0, right? So let's call it equation number 4, which is, by the way, just one variable. So we can use this now in 3. So use 4 in 3 to eliminate x. So it will be 0 plus 5z equals to 40, which is 5z equals to 40, and z equals to, divide both sides by 5 and you get 8. And that's it, right? We got all the we got values of all variables. So y is 3 here, x is 0 here, and finally we have z equals to 8. So that is our solution, right? Whenever all 3 equations are combined to find x, y, z values, that's it, right? X equals to 0, y equals to 3, and z equals to 8 is the solution to the system of equations. Sometimes in this process you might end up with a contradiction. That means something that's always false. Something like, 0 equals 1, like this. These are called contradictions, right? So if you run into these kind of situations, solution, or you can run into identities like 1 equals to 1, or -2 equals to -2. So if you run into these kind of situations, the solution is all real numbers, right? Solution is all real, solution is infinitely many, let me say. Infinitely many, since we have 3 variables. You can't just say all real numbers, right? Okay. We got our solution 0, 3, 8. So that is 0 and 3, 8. Yes. So this is the dependent situation, is when there are infinite solutions, and inconsistent situation is when there is no solution, right? There is this, they are also called dependent